The Conatory transport vehicle carrying supplies to the International Space Station is carrying a lot of supplies for science on board, including a large astrophysics mission coming up unpressurized on the exposed pallet. The Calorimetric Electron Telescope, known as CALET, is destined for the outboard end of Kibo, out on the exposed facility, for a study of high-energy cosmic rays. And today we learn more about that from Dr. John Wefel. He's a professor emeritus at Louisiana State University's Department of Physics and Astronomy and a co-investigator on the CALET team that's led by Dr. Shoji Tori of Waseda University in Japan. Explain to us how this telescope works. I mean, how does it go about searching for cosmic rays?
Okay, well, cosmic rays come at you from all directions and all of the time because they originate outside our solar system elsewhere in the galaxy. So what we basically do is sit there and just look. So it's a long exposure every time one of these high-energy cosmic rays comes at us, and it starts triggering the instrument. Then we record it, add it to the data set, and eventually we will build up enough statistics to analyze for all the things that we're interested in.
I guess that's the question then. What is it are you interested in? From an astrophysicist, what's the value of knowing about cosmic rays?
Okay, well, cosmic rays are the highest energy particles known in the universe. Nature somehow accelerates cosmic rays to vast energies, far higher than we can do at the biggest accelerator, for example, the LHC at CERN. And what we're interested in is A, how they do that, and B, what material is being accelerated? Where did this stuff come from? And so to do that, what we want to do is we want to measure the composition. We want to know how many electrons are there, how many protons, how many helium, carbon, nitrogen, oxygen, iron, etc., to try to piece together this whole question of how nature does this massive acceleration and how it ejects these particles that have been with us in our solar system for billions of years based on the old meteorite measurements. So they're a standard part of our environment.
Hey, you're taking a census of what's out there.
We're trying to take a census of what's out there, but we're trying to take it at higher energies than it's ever been taken before, and that's the key. As you move to the higher and higher energy, that's where we're beginning to see now, that's where the action is starting to show up.
Well, one of the stated goals here is you're using this to address the existence of dark matter. How does measuring cosmic rays help you do that?
Well, the whole idea here is that if there are dark matter particles out there of one sort or another, and they're their own antiparticles, so they annihilate with each other. When they do that, they turn into normal particles, i.e. they turn into electron-positron pairs, or they turn into proton-antiprotons, or they turn into various kinds of W bosons, things like that. But when they do that, their mass energy, their rest mass, becomes their kinetic energy. So they suddenly appear at these very, very high energies as a particle zipping around just like the cosmic rays. So the idea is you may be able to find them within the cosmic ray beam. Now, to do that, we have to look and see if we can find some kind of anomaly in the electron plus positron spectrum, or we also have a capability to measure very high energy gamma rays, see if we can find a signature in the gamma ray region at these ultra high energies.
I also read that you're interested in finding what it says are nearby sources of high energy cosmic rays. I mean, how close are you looking?
Okay, well, nearby is has to be viewed in an astronomer's terms, if you will. What we're basically looking for is sources that are within about 1,000 parsecs of the solar system and are less than about 10 to the 5th years old, less than about 100,000 years old. Why is that? Well, the reason is that at that electrons, unlike protons and other particles, they lose energy via inverse Compton and synchrotron processes as they move through the galaxy, interacting with matter, photons, and magnetic fields, and they lose energy at a phenomenal rate. What that means is that these very high energies, they can't travel very far before they're totally degraded. Thus, anything we see has to be coming from somewhat relatively nearby, otherwise it would just never get here from there. So in that sense, what you do is then you sit around and you say, well, what's out there within a kiloparsec from us? And you find things like supernova remnants, monogem supernova remnant, Cygnus loop, the Vela supernova remnant, and you say, well, could these be producing high-energy electrons? And so you go back to some of the theories and do some more calculations, and you come out with, yes, they could be. Maybe not, but they could be. So the idea being, if we can see one of these sources sticking up above the normal background of all the other electron positrons that we're seeing, we would be able to actually pinpoint for the first time, a source of charged particle acceleration that was in our relatively nearby or our close solar neighborhood, you might say. That would give us something phenomenal to study, because then we could go out and look and see what these particular objects, if we can pin it down, are actually doing in detail, and learn a whole lot about what makes them tick.
Well, so, Dr. Wefel, good luck. We'll be interested to see it fly and see it go to work.
And we are equally as well interested in a successful launch and starting to get some data after all these years. So thank you very much.
Thank you. Dr. John Wefel is Professor Emeritus at Louisiana State University and one of the co-investigators on the CALET experiment.